Good afternoon, and this is my presentation on screws. So whether whether you're an engineer, a doctor, or anyone with a screwdriver, then most likely you have encountered one of these screw shapes before. So if you want to know where screws began, it all began with this scientist called Archimedes. So Archimedes wanted to fetch water and decided to try something um, revolutionary. So he designed threads, like as the ones seen in any of these here, and these threads were put into a well. So once the threads rotated, the wedge shape would push the water upwards, and this was how they used to get water from wells. So in 1779, a scientist decided to put in an opposing force at the top of this wedge design, so that instead of the water being brought up, the entire screw would be pushed downwards. And by using a mechanism at the top, which is a driver, he made a slot for it, which can be used to turn this entire top in the opposite direction of the threads so that it moves the screw downwards. And that is where the entire screw began. So with that said, the first screw design was the flat screw, and the flat screw has got some certain advantages to it. One, the flat screw is cheap. That means it is easy to manufacture and it's also easy to implement. And the second thing that uh, you get when you're designing the flat screw is that the flat screw does not have self uh, centering. So this means that if you were to use a flat screw and the screwdriver pivots on one side of the screw, like here, well, let me just make that more visible, like here, the screw would turn and go in that direction. Or if it's made to be here, the screw would turn in that direction. So this means, so without the self-centering mechanism, the flat screw was not very efficient in terms of precision uh, motion and yeah, precision direction. So what they decided to do was to try and make a screw that can overcome these challenges. But the biggest problem with the flat screw was that it did not have, it had something called come out. So as you can tell, it comes out. The screwdriver does slip from the screw itself, and once the screwdriver slips out, it means that it's not efficient, especially if you're using a machine to drive in the screwdriver into a socket or a wall. So these are the reasons why the flat screw has been outdated. And then in came Phillips, who designed the Phillips screw. And the Phillips screw has got some certain advantages that the flat screw did not have. Like one, the screw is self-centering. This means that the screw would adjust itself and it would actually screw it in. Now the second feature that was made was due to its conical shape, the screw had a maximum torque. And this maximum torque would mean that when you're driving in the screw into a wall, once it reaches a certain torque, the screwdriver would spiral out and prevent over torquing of the screw, so it will not damage the equipment or the screw itself. And the third reason why the Phillips screw was revolutionary was that it did not have the come out. It did have come out, but it was not as extreme as the flat screw. Now, this Phillips screw is now technically what was used in medical implants after the flat screw failed in terms of the screwdriver slipping and also bone damage due to over torquing. And so the Phillips screw kept on being used for a while until it was no longer applicable. And now we are dealing with the hex screw. So the hex screw or Allen screw is octagonal. It's a hexagonal shape. The 6 sides, as you can see there. And with these 6 sides, if you are to rotate this octagon just a little bit more, this line would be here. That means if you are to look at the contact region, let me just make that clear. If you are to look at the contact region between the plane and the newly adjusted plane, the area is very small. So this means that the hex screw, even though it is easier to put in, and it also does have directional it also does have directionality. The problem with this screw is that it had or it has a very small contact region between the screwdriver and the screw itself, which makes it very vulnerable to damage. And this is why when most hex screws are being used in high tension regions, when you're removing the screw, even though it has a lower removal torque, it does wear out and become a circle. So make to revise this screwdriver, the new screwdriver that people are using nowadays is the torque screw. And the torque screw is like the hex screw. It does have 6 points, but it also has greater contact regions where the screwdriver and the screw meet, and this makes it more stable, especially, and so its applications is in the medical field, and then also it also has applications in electronics, microelectronics as well, to hold the sensitive components down. So with these common screw heads, I decided to go ahead and take a look at how or different patterns where the screws are made. And this is one patent of a screw head that was never really implemented. And this screw head did spring up some ideas on the kind of screw heads that we can design so that we can overcome the challenges of the hex screw, which are the biggest challenge that we have for the hex screw currently is the damage that you get, the damaged equipment. That is the damaged screw head and the damaged screwdriver. So this is the biggest problem that most surgeons face. But the biggest advantage that the hex screw has, or the multi-level hex screw for that matter, is that it does have very high directional torque, which means if you're screwing in the hex screw from its screw axis, the torque is high. But if you are to screw in the same screw from different direction, the tension or the resultant force is not very different between these two screws, unlike the Phillips screw, where any small directional change will result in drop in resultant force. So this is the only advantage that the hex screw has, and that's the reason why it is mostly used in medical applications. For example, if you are trying to screw in a pedicle screw, which has a multi-level hexagonal design, because of this directional input variance, you can actually screw in to a particular bone manually without causing a lot of tension or stress on the bone, and without losing grip on the screw itself. So if we were to look at these two, one of the designs that did come up to mind was to look at different patterns. And by far, trying to look at all the patterns, there were not many, but this was one design that could have achieved the first criteria to knock out the hex screws, but for directionality, there were not really any other options, which I did explore, but I will do more on that this coming week. Anyway, that is my presentation so far. Thank you.